Writing formulas for polynomial functions. Now that we know how to find zeros of polynomial functions, we can use them to write formulas based on graphs. Because a polynomial function written in factored form will have an x-intercept where each factor is equal to 0, we can form a function that will pass through a set of x-intercepts by introducing a corresponding set of factors. Factored form of polynomials. If a polynomial of lowest degree p has horizontal intercepts at x equals x1, x subscript 2, all the way to x subscript n, then the polynomial can be written in the factored form f of x, which is equal to a times x minus x1 to whatever the multiplicity is of that, x minus x2, whatever the multiplicity of that, all the way to x minus x subscript n, with the multiplicity according to x subscript n. So again, the powers p on each factor can be determined by the behavior of the graph and corresponding intercept. And the stretch factor a can be determined given a value of the function other than the x-intercept. So given a graph of a polynomial function, write a formula for the function. Number 1, we identify the x-intercepts of the graph to find the factors of the polynomial. Number 2, examine the behavior of the graph at the x-intercepts to determine the multiplicity of each factor. Number 3, find the polynomial of least degree containing all the factors found in the previous step. And number 4, use any other point on the graph. The y-intercept may be easiest to determine the stretch factor. So for example number 10, we're going to write a formula for a polynomial function from the graph. We're going to write a formula for the polynomial function shown. So the first thing we want to do is look at the graph and then find out where are the x and y intercepts. So there's an x-intercept here at -3. And we have a y-intercept at 0, -2. And then we have another x-intercept at 2. And another x-intercept at 5. So again, we have -3, 0 here, 2, 0, and then 5, 0. Okay, so let's take a look at the behavior around the x-axis. So here, this line is going straight through, which means it has a multiplicity of 1. Over here at 2, 0, we can see that it bounces. And so it's not that flat, so we can see that it's possible that it has a multiplicity of 2. And then over here at 5, 0, it's going through at once without flattening out, so that means it's a multiplicity of 1. So this graph again has 3 x-intercepts. X equals -3, +2, and 5. And the y-intercept is located at 0, -2. At x equals -3 and x equals 5, the graph passes through the x-axis linearly, suggesting the corresponding factors of polynomial will be linear, so that means it has a multiplicity of 1. At x equals 2, the graph bounces at the intercept, suggesting that the corresponding factor of the polynomial will be second degree, quadratic. Together, this gives us the following. First x-intercept is -3, the second x-intercept is 2, and the third x-intercept is 5. So, in step 3, we're going to write out what that form represents. We have f of x, which is equal to a times x minus the first x-intercept, and that had a multiplicity of 1, and then x minus the second intercept, which had a multiplicity of 2, times x minus the third x-intercept, which had a multiplicity of 1. So now we're going to plug in the values of x1, x2, and x3. So we have f of x, which is equal to a times x minus a -3, times x minus a +2 squared, times x minus a +5. Now if we simplify that a little further, we're going to get f of x, which is equal to a times x plus 3, times x minus 2 squared, times x minus 5. So we're not entirely finished because we need to figure out what is the stretch factor here, meaning a. Okay, so what we need to do is we need to know what the y-intercept is from the graph for us to be able to figure out what a is. Now again, remember that the intercept from the graph was 0, -2. So we're going to use this as an ordered pair to determine what a is. So for step 5, to determine the stretch factor, we utilize again another point on the graph. So we're going to use the y-intercept 0, -2 to solve for a. So now using what we have in step 3, we're going to let x equal 0 and we're going to let f of x equal -2. So f of x becomes -2. We're going to plug in 0 for x and solve for a. So we have -2 on the left side equals a. Well, 0 plus 3 gives you 3. 0 minus 2 squared gives you +4. And 0 minus 5 gives you -5. So we have -2 on the left side, which is equal to 3 times 4 times -5, which is -60a. Divide both sides by -60. We then see that a is equal to reduced to 1 over 30. So now we know what the stretch factor is into this function. So we're going to replace a now to be 1 over 30. So we're going to get f of x, which is equal to 1 over 30 times x plus 3 times x minus 2 squared times x minus 5. And so therefore the graph polynomial appears to represent the function f of x, which is equal to 1 over 30 times x plus 3 times x minus 2 squared times x minus